will be posted on the PYRN website. So for those of you who submitted or requested to have certificates, just make sure that you submit your full names and maybe check your email and your junk if you haven't received it. So I'd like to thank everyone for joining today. We have a mix of academia and industry, so it's a good turnout. My name is Zachary McDonald-Ducharme. So today we have our PYRN president, Natalie Arapin. Emma Cameron will be moderating, and we have other PYRN committee staff here with us on screen. I'd like to thank everyone involved in putting this webinar together, and I ask that people would save their questions for the end. You can post it in the chat or wait for the question period, and we'll try and get to as many people as we can. Okay. So I'd like to introduce the PYRN president, Natalie Arapin. She has a few words to say.
Hi, everyone. Thank you so much for coming to our first webinar of 2025. We're glad to see such a wonderful turnout. For those of you who are new to PYRN, we're a research network underneath the International Permafrost Association, attempting to connect young researchers and early career professionals who are interested or a part of the permafrost science and engineering community. We are hosting technical webinars monthly. There's newsletters that go out. We host events at conferences. So if you're not yet a member of our network, I highly encourage you to sign up on the PYRN website so that you can stay in the loop as to what we will be doing in the future. Thanks so much, Zach and Emma, for your efforts in putting this together, and I will pass it on over to you.
Thank you. So permafrost models are used by researchers, engineers, climate scientists, geologists, and other professionals to predict the behavior of permafrost under varying conditions. Those who work in permafrost modeling compare simulations with empirical observations to better understand what the governing factors are and how changing these factors affect permafrost. Modeling is a very prominent topic in research today due to the improvements we see in hardware and software capabilities. And it's useful for its ability to scale in size and different periods of observation. A good model will never completely align with reality, but it does provide industry professionals with a low-cost alternative to understanding and predicting permafrost behavior in a changing environment. So I'd like to introduce our presenters today. Today we have Stephan Gruber and Mehdi Pouragha. They come from two different fields of expertise. Dr. Stephan Gruber is a professor of physical geography at Carleton University, specializing in mountain and polar environments. Dr. Mehdi Pouragha is an associate professor of civil engineering at Carleton University, specializing in constitutive modeling and geomechanics in cold regions. Both Stephan and Mehdi have a shared interest in permafrost and ground temperature modeling and are at the cutting edge of applying the current tools available to better understand the governing factors. A main theme of this presentation will focus on collaboration in research and industry as people with different backgrounds and different interests work together to develop a better defined and more robust understanding of permafrost and permafrost modeling. So thank you very much for agreeing to be part of this panel today, Stephan and Mehdi.
My pleasure.
So I would like to start with this slide. I think this slide perfectly encapsulates everything we want to talk about today. And I'd like to start with you, Stephan, if you could kind of talk about how these three different spheres overlap.
Yeah, I think what we're faced with, and I don't know if you're able to go for just 1 minute to the one slide that we have that I showed you last with like the transient climate, because I think that makes the point really well.
Like one of the last slides? Okay, I'll go to the end. Is it this one?
Yes.
Okay.
So if we look on the lower left, we have one way of rendering what global climate has done over the past 150 years, roughly. And so we see that we have like about 4 decades, 3 decades of consistent warming. And we expect from what we know about climate and what we know from climate scenarios that this warming is going to continue in the future over many decades and possibly centuries. If we look back, however, from the beginning of this warming, say from the 1980s or so, we look backward, we see a period that was more or less stable. And so when we're working in our respective disciplines and disciplines and silos are good because they help us to work in consistent conceptual frameworks, we can establish what we would call best practice, things that have shown to work in tackling particular problems. And best practice is a bit backward looking, right? We say these things have worked in the past, so most likely they work in the future. Now we are now at the, past 2020. The world is warming, the north is warming even faster. I mean, I don't have to repeat this to the choir here. Permafrost, by and large, is thawing and will be in a persistent, pervasive state of thaw for a long time. And that is fundamentally a new problem for us to tackle. Our planet is going into a condition that as a species, humans, Homo sapiens, we haven't seen before. And that includes, engineering knowledge and science and so on. If we can go back to this kind of little Venn diagram,
Yep.
Zach, so that also means that we're faced with new problems today that we didn't have before. And so these three blobs here, infrastructure and land use, could be how do we plan a road, a building? How do even, traditional societies think about how to travel on the land? There's a whole lot of things involved here that works really well if we don't have large changes because we can use the knowledge that we have. If we think about climate events or trends, extreme weather, this is also something where we have a lot of experience. I mean, everybody of us probably has a smartphone, and this smartphone has weather forecasting apps. We know how those things work. And then there are a few emerging things now for climate change where countries and like other multinational jurisdictions start to provide services to think about, well, how is climate changing? What do we need to adapt to? How does the terrestrial environment change in terms of more forest fires, things getting wetter, more snow, less snow? And these spheres interact, particularly strongly when we think about hazards in permafrost areas, right? And so if we're just thinking about how construction worked in the past, we can no longer do this. So somehow we need a time axis that comes from climate. Part of that might also come to what we do to the ground surface. But we also need an axis that's maybe more geology based. That is, well, what is in the ground? What is the geotechnical situation that we have? Is there ice in the ground or not? And we have different parts of those disciplines say, well, we can have the solution. I would frame today's discussion around we will only find good solutions if we find mindsets and technologies and conceptual frameworks that allow us to work in this intersection and think about how can we use what we have already better together and what are the novel things we need that none of these disciplines at the moment have.
Thanks for the very elaborate answer. That was great. Mehdi, would you be able to add to Stephan's comments and just point to what you think are the current barriers to achieving these this overlap of knowledge?
Yes. So Stefan covered it quite well. I'll add something to his last point. Something that we have to also figure out is that what we already know, and I know what we already know in geotechnical engineering because that's my field, but working on something as comprehensive as permafrost requires me to understand well beyond that to find out what knowledge exists in different fields so that I don't reinvent the wheel. And believe it or not, that's not as easy as it sounds, because things are called different things. The same thing is called different things in different fields, different formulation, different mathematics, different concepts, procedures. So something as simple as figuring out what we know already is also a challenge right now.
So
in
you'd
this
say like barriers to communication, or just
Yeah,
an unwillingness maybe to
it's not non-willingness. It's just this topic is it requires a working of different disciplines with each other, really. And with the sort of urgency that it has, you don't have the luxury of waiting for this to happen. So,
So do
um,
you see these barriers kind of slowly dissolving with time?
yes, and I hope that it dissolves more and more with uh, people coming together from different disciplines in conferences and meetings, and also being willing to uh, start a discussion. We have to get out of our comfort zones, intellectual comfort zones, or our disciplines to do that.
Okay. So I guess we could start with technologies. What are the new technologies that are being applied today for ground temperature monitoring? So I guess this will be directed at Stefan first most. What would you say the biggest improvements are on current technologies from previous?
Maybe it would be good to think about technologies and approaches, because in the end of the day, what we get out of our ground temperature measurements is strongly predicated by how do we plan those campaigns and what are our aims. So what technology brought over the last maybe 30 years or so that I've been following this, and I want to give a disclaimer because I'm involved with a German company that actually makes data logging systems, and I own a company in Canada that sells them, right? So treat everything I say with suspicion. But something that has happened over the last decades is that data logging systems have shrunk in size. So what used to be the size of a microwave and very, very cumbersome now, is the size of a cigar. And you can have data loggers that function for 10 years that you can read out wirelessly at the distance of whatever, 10 or 30 meters, that are small and easy to handle. There are data loggers that are the size of a button, called iButtons, that don't last quite as long, are not as accurate, but they're very, very cheap. There are other systems that communicate via, larger wireless networks, LoRa, LTE, satellite communication. So we have a much larger budget to choose from, right? And then there's things that we can do in research. Like 15 years ago in Switzerland, I was part of a very large research network between, let's say, geocryology and electronic engineering. And we had networks with between 2,000 and 3,000 sensing channels, very high up in the mountains that were measuring every 2 minutes, right? And like a lot of additional things were measured that are phenomenal in a research context. And I think when we're more practical, how we choose these technologies depends on what we want. For example, in Switzerland, I used to operate a field site with 400 iButtons. They were cheap, but they needed to be read out every year. And I could do this because there were a lot of students and going to the field was safe and a matter of a 4-hour train journey. Now, when I came to Canada and the field site that you see here was instrumented, and I knew I would only be able to go every 4 years or maybe less. You don't want to lose all your measurements because your data loggers can't wait for an additional year. And so all of a sudden, you choose something that has a longer battery and memory life, right? In this larger research cluster here, we have about 230 data loggers that are measuring. And because they can be read out at short distance wirelessly, we can read all of them out with like 2 people in a helicopter in 2 days, right? We couldn't do that with iButtons. But if we wanted to have a satellite uplink for each of them, we couldn't pay that. right? So there's a trade-off a little bit in what we want to sample. And then I think if I just say one more thing here, in the past, let's say 30, 40 years ago, many boreholes were logged manually, where there's thermistors in a borehole and someone goes with a multimeter and then has calibration curves. And the effort for someone to measure today is simply no longer really worth the time, because the cost of data logging systems has come down so far. In what you see here, the data logger is actually suspended inside the borehole tube, right? They're very, very small. They cost a couple hundred, or with the thermistor chain, a couple $1,000s. That's almost the same cost as flying someone there to do the readout. And then there's a recognition that the temperature at this near the ground surface, if you look at the middle of this graph here, you see kind of a temperature envelope. At the height of 0 is the ground surface, and then below in blue you have the minimum temperatures, in red the maximum temperatures. This is something that we probably all know and love as permafrost researchers or engineers. And then close to the surface there are those 4 triangles. So those 4 triangles are 4 individual small data loggers that have been distributed around the borehole in a radius, within about 10-meter radius. And it recognizes that the ground surface temperature is very variable in space. If you look at the photo, you see like mud boils, you see rocks that were heaved up, you see different sizes of shrubs. But the ground surface temperature is very, very cheap. We don't need a helicopter to transport a drill and a drill crew or all of those things. And it turns out that for testing models, the biggest uncertainty for us comes from, do we understand what the ground surface temperature is? And much less comes from what's happening in a subsurface. So there are a few things that don't relate necessarily to technology, but to the approaches. How do we then use the technology to learn from it?
Going to Mehdi, would you say that there's a lot of overlap with what they do in physical geography with geotechnical engineering?
In terms of,
In terms of technology, are there pieces of technology that are unique to geotechnical engineering?
certainly, I think they mostly complement each other than having overlaps. So for geotechnical studies, we have 2 main ways. You can do in situ, infill, or you can take a sample, like boring and taking a sample. And they have their own difficulties and accuracies. Having a borehole is shared with geophysics. You're going to bore something, you can take, if you're careful enough, you can take the sample out. But then we have our geotechnical test. Do you want me to go over a geotechnical test?
Just briefly from
Okay.
materials
So,
testing, I suppose.
So for cold region, what people have done is first to modify and adapt the techniques that we had in conventional geotechnical investigation to cold region. Like CPT is something that has been used in geotechnical engineering for years. It needed to be modified a little bit. Temperature measurements have been added to some of those apparatus, but people have shown that they can be used, and if you modify recalibrate everything, it could be used for frozen ground, even for ice or snow. You can use CPT. It's relatively cheap, easy to carry. So that's what we have been relying on if we didn't have the luxury of taking a sample. For things more accurate, we need to sample one way or another. And for the frozen systems like permafrost, retaining the temperature is a challenge. So basically taking undisturbed samples. Yeah, I know you know that, Zach, firsthand.
Yeah.
Taking undisturbed sample is very, very challenging. You have all the challenges that you have for conventional geotechnical engineering if you want to take an undisturbed sample of, let's say, a clay. But on top of that, now you have all the temperature changes that you can induce just by drilling and
Yeah.
exposing it to air.
Well, we talk more about that in the logistics
Mhm.
section, but it's just getting it there in the first place.
Yeah. And then
Sorry.
if we do have the sample, then it becomes the matter of having right temperature controls for our conventional tests like traction tests. We do traction tests, but now we have to do traction tests under controlled temperatures. The accuracy of these tests, they have been improving over the years now. There are labs, including in Canada, can do very reasonable control on temperature while they're doing the traction test. I can go into other methods that has been recently.
Like we can go over it again in
Mhm.
the logistics part.
Sure.
Would you be able to comment on this very briefly, Stephan, about the surface offset?
Yeah, if you just very briefly go back one slide.
Okay. Sounds good.
Sorry about that. So basically what you see on the left-hand side here is with these pieces of lath in the ground, that's like what we call a plot that's measured with those 4 data loggers. And the graphic in the middle, the 3 triangles show the mean annual temperatures of those data loggers. And then a bit further up in that graph on the left, you see 4 little circles that are the mean annual air temperature measured by a contraption that you see on the right-hand side. These are kind of the same type of data loggers, but slightly modified for air temperature. And so we call the surface offset the difference between what the air temperature is in the region. So the air temperature stays relatively constant in space, at least on temporal averages, but the surface is very different. Right? And so now what we see in the next slide in this histogram is the difference between the circles, the mean of the circles, and those triangles. And what we see here is we have a range from about 0 to 11. That means within a couple kilometers horizontal distance, just walking distance, if you take the blue or the red here, the mean annual ground surface temperature varies by 11 degrees. It could be the same temperature as the air, or it could be 11 degrees more. That difference in temperature, like 11 degrees, is almost the same difference in temperature as you have between a mean annual air temperature in Yellowknife and in Ottawa. So that tells us there's tremendous local variation. And this is why measuring and understanding this ground surface temperature is important. And there was this first slide that you had, Zach, with a mountain that said spatial heterogeneity and spatial trajectories. The graph on the left I've made quite some time ago because it's kind of easy to understand this in Switzerland, right? So this is an area of Switzerland where in the valley people grow wine for a living. And on the high peaks, there's permafrost, there's glaciers, there's research stations that are very nice. And so a high resolution, regional climate model or reanalysis would have a grid size similar to this floating yellow surface here. And so this immediately tells us, yes, of course, if we go up and down, there's going to be a different air temperature. And if we're on the south and on the north side, there are differences, right? So for mountains, the spatial heterogeneity becomes quite intuitive. But then on the right-hand side is a photo from the area around Lac de Gras. This is the haul road of the Ekati diamond mine, where the measurements I've shown before were made. And in this area, you see on the right-hand side here, the difference between different places on the ground on the annual average is those 11 degrees, right? And this is the difference we have to unravel. And of course, this temperature difference arises from ground properties, hydrology, snow, radiation. And so we can't assume that we have this difference, it's fixed in time, and then when climate changes, the pattern just gets translated into everything is 3 degrees warmer. These are wildly varying trajectories. And that's what we need to figure out in order to force simulations of what happens in the ground surface when permafrost thaw translates temperature change into the hazards that we care about.
Okay,
And
well,
that's what we see in this histogram. is just a difference between two different years, individual years.
I think that'd be a good transition into modeling. Yeah, we talked briefly about logistics, but we can skip this slide. So I guess start again with Stephan. What would you say makes a good model? And I'm going to ask the same to you, Mehdi, from a physical geographer point of view. And how is that different for from the geotechnical engineering point of view?
Well, then if I start and Mehdi can say whether and if there are differences, I would say what makes a good model is informed simplification. And we have to think about that these models are long chains. So if I think about there's a model that can describe how frozen soil warms and changes in stability, this is completely Mehdi's domain, right? But then if I can't describe what forces this change, if I can't describe the surface temperature change, then this is not going to be good. So I need to be able to describe what's in a subsurface and in a surface in terms of characterizing it, but also in terms of representing what is relevant in my model. Not representing as much as I can, not representing what I love most to represent because I've done it all my life, really figuring out what is the menu of things that might be relevant, what are the menu of models that I have, and making an informed decision. And that is super, super scary and difficult. But then these models need to be driven with transient atmospheric information because we're thinking about change. Well, how many places in the north do we know that have meteo stations that give us decades of uninterrupted data? Very few. So we need to rely on global weather models and reanalyses. And applying that data isn't all that easy. That's applying another model. If we want to have climate scenarios, we first need to select, debias those climate scenarios, and then apply them. So there's a long chain. And very often what we do is we pick out the first thing we have available and do something. And so for me, a good model is one where we have a very well-informed simplification for the entire chain. Because like all chains, the simulation chain is breaking with the weakest link where we're not paying attention.
Would you say, sorry, would you say that it differs between research and industry? Would you say that how would you be able to speak to the people from industry in the audience?
I don't think it should differ, right? Because we want to do things well. I don't think the model, whether it's done by an academic or by someone in the industry, is going to be better or worse. I don't think there are magical abilities in the industry or in academia. I do think that going back to the analogy of the chain where the weakest link breaks everything, we had this Venn diagram with those three domains, right? And the chains kind of include all of those domains.
Okay.
And my impression is that a lot of times in industry, there is a focus on best practice. And here's how we can show how well we're doing. Because time is pressing and the client doesn't want to have astronomical bills. In academia, part of our job is actually to look at like how bad are we doing and how can we improve, right? So it's easier for us to focus on that. And so having the conversation, I think, between practitioners and academia might actually help speed up what we could call next practice. Not what worked in the past, but what do we think today will work well ahead of time?
And Mehdi, would you say that all the points that Stephan brought up are translatable for the geotechnical engineering side of the modeling?
Yes, certainly it's general enough that it's translatable, especially the dialogue between academia and industry. One thing I want to say is that, so I said that you have to translate things between disciplines. One thing that I get usually anxious is when people say model. Like it can mean a lot of things when you say model. You can say physical model, and that means doing experiments. That's that is still a model of reality. That's not the reality, because you're simplifying what's happening to whatever you're sampling. For me, a good model has a couple of characteristics it should have. Like you should know, first of all, what is the physics that you want to model. Like in conventional geotechnical engineering, we usually don't care about temperature. So thermal, diffusion, what's happening to temperature is not a physics that a traditional geotechnical engineer would be modeling, right? But here in permafrost, we have to consider that. So having a list of physics that you want to consider is where we start. And then we have a different kind of model, which is called constitutive model. What is the behavior of the thing that I want to put into my simulation? Because you can have the best simulation in the world. If the material model is wrong, then it's garbage in, garbage out. And that model that you're putting in should also conform with the physics that you are modeling, right? As a geotechnical engineer, when I'm modeling permafrost, I cannot just rely on more Coulomb that I'm used to have. Now things are going to depend on temperature. I have to make sure that I'm doing that right. Then comes what method you use for doing computational, if it's finite element or anything. But in between there is something that is really important. That is the boundary condition. And that's what Stephan was mentioning. Like, I can do all the things right, but at the end of the day, what is going to derive my model is the boundary condition. And we need to have the right boundary condition to be able to understand what's happening. And hopefully from there, we can use our model to generalize into the future or different locations. I'm not sure if I really answered your question, or I
No,
answered
you
a
did.
different question.
I wonder, well, we do go into more modeling. Let's see, we have a couple slides here.
Right.
Simulations. We go into numerical modeling.
Right.
I guess for people who don't work in modeling, what is a boundary condition?
Okay. Boundary condition is when you want to model a system, usually what's going to, we are going to isolate a system to understand. I'm going to say the whole permafrost is difficult to understand. I'm going to take a sample out and understand that. And that system, I call it a system, that system interacts with its environment, right? That interaction is boundary condition. Now we have to sort of understand that interaction and introduce it into our models.
Okay. So I guess this segues into numerical modeling, which is your bread and butter. I believe this was one of your studies, but what are the applications of numerical modeling in software?
Numerical modeling in softwares, you mean, or in
Sorry, yeah,
permafrost?
I didn't phrase that correctly.
Yeah. So do you mean permafrost, science and engineering, or in general?
I'd say let's focus it on permafrost.
Okay. I think it's better to go to the slide with finite element, the ice wedges slide that
This
we
one.
have.
Yeah.
No, the ice wedges.
Oh, ice wedge?
Yeah.
Oh, okay. There you go.
Yeah, that one. This is a computational simulation, computational model that Stephan and I with Gabrielle we developed, and it uses finite element, extended finite element to model something, to model the development of ice wedges. Now, Here we have finite element. Finite element is a computational method to solve differential equations, including how temperature changes, how heat moves in a system, or how something that is deformable deforms under loads. And that's what we are doing here. We have temperature and we have load. And the good thing about this software is that we only have to say what's happening at the boundary condition, and then it tells you what's happening with time inside the whole domain. For instance, here, going back to what Stephan said, you have to find the right simplification. So one simplification we're making here is to assume that this question can be reduced to 2 dimensions instead of 3. We're doing a 2D simulation of the ground that is under sub-zero temperatures. Temperatures are applied at the top with a lot of consideration that Stephan would know much better than I do. I've learned these things from Stephan. And then, so the conventional finite element that people use for figuring out deformation needs to be extended now, because now we want to see something. We want to see cracks in the ground. So then people extended this method, and it's literally called extended finite element, XFEM, that can actually capture, as you're pointing now, the development of cracks in the ground. Right.
So it's discontinuous here? Yes.
So this method was developed for modeling cracks in metals, but now we are adapting it to model ice wedge formation. This is an example of finding things in different fields that can be applied to what we observe in permafrost.
And conventional FEM doesn't deal with discontinuities, so that's
No,
why
it cannot.
XFEM was used. Okay. And what's the significance of reducing a dimension, going from 3 dimensions to 2 dimensions? Does that impact?
Yeah. This is the art of modeling, as Stephan said. You have to know what to ignore, of what simplification to make, and still get something meaningful out of it. So first of all, the first thing is to make sure that if you go a dimension up, the computational cost goes up pretty quickly. And not only that, sometimes the computation methods don't exist in higher dimensions. Like XFEM, extending it to 3D is not that easy. It's not been done, at least we don't have reliable packages that can do that. Sometimes we have to make those. This is what I mean. Sometimes we have to stick to the tools that we have. But sometimes we sort of say, okay, in the third direction, maybe we can have symmetries, right? Because if you look at soil, it's usually axisymmetric, right? So things are in vertical direction, things change, but usually in horizontal direction, you can assume that the change is not as drastic as in the vertical direction. So maybe reducing it to 2D is not a big deal. But then at the end of the day, what happens is that you're going to do that and see if the results that you get make sense or not.
Okay.
If you're making a very bad assumption at the beginning, you will see a big difference.
Did you want to add anything to that, Stephan?
No.
Okay. See if I guess we'll go back to the beginning.
Sorry for jumping around. Yeah.
So in that same vein, you mentioned constitutive modeling before. What is constitutive modeling?
Oh, well, so if you talk about numerical simulation first, you can probably understand it there. May I ask you to go back to that?
Sorry, yeah.
XFEM or
XFEM? Gotcha.
Yes, please.
Okay.
So this is really done with a mesh in the background. You don't see it here, but there is a mesh. So this whole area is divided into smaller cells, and then the calculation is done for those cells. Now, why are we doing that? Because, for instance, what you're seeing here is a distribution of a stress. You see the colors and their stresses, right? What we understand in the lab, when we take a sample under actual test, we understand how that sample behaves under one stress and one strain, right? We assume that the stress and the strains are the same for that sample.
For the
And then
non-engineers, what are stresses and strains?
a stress is how strong we're pushing something, and a strain is how is a measure of deformation of it. And for mechanics, at least in engineering mechanics, when we say mechanics, it's usually the relation between a stress and a strain. And the stiffness comes in between. How stiff something is, how resistant it is to forces in terms of deformation. All right. So then what we need to understand is how one of those small cells behave first, right? The software does not know that. The computational method does not know that. The computational method asks you, tell me how one cell behaves, and I can repeat this for all the cells. But it's still on us to tell the software how one cell behaves, right? That is the constitutive model. Now, I'm using behave because it doesn't need to be mechanical. Like in Stephan's word, they do a lot of heat diffusion equation. Now, the conductivity there is a constitutive model. The heat diffusion, you're making constitutive assumptions.
So I guess we can move on to this. What would you say how some of your more recent publications have helped solve specific challenges in permafrost research?
Yeah. So one problem we're dealing with is extreme variability of material. Like we had that problem for soils as well. Now you put on top of it temperature, ice content, all the things are new now, right? So it quickly becomes next to impossible to reliably characterize a site.
So it's hard to create localized predictions because things are different from one location to the other. Okay.
Yeah. Then one method to tackle this problem is to do what we call a multi-scale modeling. And what that means is that, okay, instead of trying to understand permafrost, the mixture of soil and ice as a mixture, can we understand soil separately and ice separately? And maybe that reduction helps us reduce that space of things that we have to explore to make sure that we understand things. Like this idea of reductionism is in science always. When things get complicated, we try to understand the constituents and then hope that we can put it back together and understand the mixture. What we have in this slide is one of our attempts to do that. This is the figure that you see in the middle right is that is under microscope. It's a capillary water in between two surfaces, two particles that you sort of see also in top left. That is also on the microscope. You see the gray area in between particles. These are liquid-like stuff held together in between particles by capillary. And then if you reduce temperature, you see that it freezes into something that is an ice bridge in between particles. This happens when saturation is low. in what we call ice poor permafrost. This happens in coastal permafrost region as well, when you have a lot of granular material with high permeability, so it doesn't retain water that well, other than holding them with capillary action. Now, the question was, maybe we can simplify this system. So again, going back to what Stephan said, the right idealization. The bottom left, you're seeing a schematic of how these things form. And if you go to the right with the spheres, that's our idealization of this system. Where we are thinking, okay, let's assume particles are a sphere. Let's assume there's an ice bond in between them. And let's assume the strength of the soil, the mixture of soil and ice, is coming from these ice bonds in between. Now, there's a lot of calculation we can do. You find the geometry of these things and relate the strength of the ice to the strength of the whole system. And I think in one of our slides, I compared these results. I'm not sure if you have it.
Is it this one? Possibly? No?
No, it has a graph in it.
I could
But
look
maybe we
around.
don't have it.
Okay.
That's fine. Maybe we don't have it. We can show that it captures a lot of the stuff that does not come naturally if you understand the mixture of soil and ice. Like it can capture. So before that, you have to test samples at different void ratios, right?
Okay.
To understand the effect of the void ratio. When you do it this way, it naturally comes out of it because it's a part of your calculation.
And
So
void ratio is a measurement of
the porosity, how much void you have in between particles compared to how much solid you have in the system.
so space or water, maybe?
It could be filled with anything. It
Okay.
could be filled with anything. So whatever that is not solid, take one of those pictures in bottom left and remove whatever is gray. What is left is void. So in this way, what we are doing is to help characterize. What we are saying is that, okay, you don't have to take the samples and do a lot of tactile tests on permafrost soil. Just understand what type of ice you're dealing with and what type of soil you're dealing with, and hopefully we can put it back together and tell you what how the mixture would behave.
So we can go over this very briefly for scaling. Mehdi, how would you say that modeling software addresses scalability? So we looked at the micro and now we're going really, really large.
Yes, so we're going both ways. We are going very, very small and very, very large. Now, scalability, different models help us capture different scales. Like finite element is larger scale usually. You're dealing with the scales that are tens of meters, hundreds of meters. And then in recent years, we have developed models that can go smaller now. I mentioned discrete element. So in discrete element, what we are doing is we are actually modeling each particle of soil individually, right? Now, 20 years ago, probably the limit for that was we could probably simulate tens of thousands of particles. But now that is quickly becoming millions, and we can do that. But still, that does not scale well to full size. That's why people in geotechnical community are now developing what we call hybrid models. And that is probably one of the newest trends in that we mix different models. You can do finite element, and inside each cell, you're running a discrete element. And these different methods are now coupled with each other. And that helps us scale now, because discrete element by itself, because you need to add all the particles. You cannot scale it to a full system. You end up with billions of particles. It's not possible to solve them, right? But then you combine that with finite element, and then you can scale it up.
So I think we'll have to move on to the collaboration portion, so we leave enough time for questions. So let's just talk briefly about the different organizations you've been a part of, Stephan, and I think Mehdi, I'm not sure if you're part of, well, I know you're involved in Create Leap, but the collaboration aspect of this presentation. What's the difference between, actually, let's first define what Permafrost Net and what Create Leap are and what their differences are.
So maybe to connect this to what we've talked about before, in the last 45 minutes or so, we've somehow come back to this topic of, well, we need to work across different knowledge domains. And there are some things we need that emerge as being new. They're not just things that we have already that we combine in different ways. And that's not so much a technological problem, but kind of like a social problem. So how do we do that we work together? How do we teach together? How do we teach new things? How do we expose each other to each other's language and so on, right? And Permafrost Net really started 8 years ago on Valentine's Day of all days. We had a large network. We had a large network meeting at Carleton University here, kind of asking 60 people from across Canada, like, what do we need to do to connect permafrost knowledge better and figure out better what needs to be done? And we've created a report, and part of that workshop was already aimed at finding money to support such a research network, right? And then, of course, a research network can never be everything for everybody, right? If it's funded, you need to make decisions who's in and like who's out and all of those things. But it doesn't draw boundaries, right, between those who are in and who are out. And the same workshop also led to the creation of the Canadian Permafrost Association. So it's kind of like a bit of a starting point for Canadian permafrost researchers, engineers, practitioners, people with an interest in permafrost, to having more contact, having more structured contact. I invite all of you to look at the website of NSERC Permafrost.net. We've been funded for 6 years. We're going to ramp down in 6 months from now. So we're at the end of the lifetime for that particular network. It's a strategic partnership network. So that means we're working between academia, government, indigenous organizations, and industry. The network funded a lot of networking, meetings, webinars, like a lot of different things. We have a network data scientist who has been instrumental in kind of creating and improving particular small pieces of infrastructure to handle permafrost data better, to do simulations better. But we've also funded about 50 or 55 graduate students and postdocs throughout the tenure of the network. So it really was a boost for permafrost research. It was a boost in some ways for permafrost research that started to connect better across, some silos that existed. And so now we're 6 years later. We have, I think, a changed conversation in Canada about how do we network permafrost knowledge. We have a lot more people involved, so the network isn't just researchers and students. There are a lot of very senior people from industry and government involved in the governance. And this is good because previously we didn't have the continued conversation with all of those people. We've had policy sessions, for example, at the Canadian Science Policy Conference and so on. So it's been a long initiative to better network and connect people involved in creating permafrost knowledge. Maybe also initiative to coming closer to speaking with a unified voice, right? Makes a big difference for people who fund initiatives, whether the community can be open and speak with a unified voice, or whether there's like different voices that might be contradicting each other. And I think there was quite a bit of momentum. And then 2 years back, we've started another network, if you will, that's Create Leap, also NSERC funded, that focuses more on training and a little bit less on the actual research. And that will train 6 successive generations of graduate students. And we've also there kind of tried to stretch open a little bit the boundaries of what NSERC intended and say, well, we're actually treating the people who instruct, including a lot of Northerners, we treat us all as people learning and coming together. And so it's a bit of an experiment to have graduate training together with people who are not from an academic background and who are not intending to get an academic degree. And it comes with like all the beauty and all the confusion and difficulties that are to be, expected when you embark on something like that.
And as I understand it, both of you are still looking for new opportunities to collaborate and get new students and in and doing some sort of collaboration between each other on future projects.
Yeah.
Yeah,
Yeah, it
definitely.
wasn't really a directed question, but I think in the interest of time, I think we should give the audience enough time for questions. We have 3 minutes. We can go a little bit over, but I want to respect everyone's time. So I don't know if anyone has any questions. I see in the chat here. Emma, so if anyone has any questions, please feel free to type it in or raise your hand, and we'll get Emma to read it out. So no questions?
No questions yet. Maybe that means
Oh,
you
well.
guys did a really good job at
You
being
answered
very
everything.
clear.
Well, sorry, well, that's the way.
Okay, well, I did have a couple of backup just in case. So how has the understanding of the factors governing permafrost changed with developments in modeling? I'll direct this towards Mehdi.
Can you repeat?
Sorry, yeah. How has the understanding of the factors governing permafrost changed with developments in modeling technology?
That's a good question. I cannot give you a definite answer because that requires me knowing everything that has happened in research, and that's really not possible. But I can give you examples, like in understanding, let's say, failures that we see in cold regions, type of failures. Traditionally, they're usually described as what we call creep, and that's slow movement of the ground. And then at some point, that velocity increases and things fail, right? Now, and then in the jargon is called primary, secondary, tertiary phases of creep. But coming back to modeling, it tells us that, well, these things are actually, they have different physics behind them. The slow movement is something else, and then when you have fast movement, it's actually material failing, which we call failure instead of just movement. Now, that changes the perspective of what's happening really. It's something, it's some mechanism that is triggering something else instead of the same mechanism going on. Now, if we want to at some point maybe intervene or stop it, then knowing what's happening would be instrumental in designing what type of intervention you can take. That's just one example that came to mind.
Well, thank you, Mehdi. I know it's 2 o'clock now, so we'll go over one more question from the chat.
Right.
So this is from Quinn. So I guess Quinn is the nickname. So she asks, you briefly tackled the challenges surrounding scale of observations and modeling and scale exclusive properties. could you elaborate further on how to choose an appropriate scale for a model? So
Ah,
that's probably Mehdi's domain.
yes, yes. That's a tough question. That's a tough question. You should just start by thinking what you want to capture, right? So if I knew what type of question you were trying to answer, then I could probably be more accurate. Um, if you're so let's say you want to if there is a town under a slope and you know that slope is going to fail, what you need to know is how much would be the runway, right? I work on characterization of unfrozen water content in soil using. Oh, so what you're working on is basically something that I would call constitutive, right? So you're working on something that is related to a small part of the um, soil, and then you can build a map out of that of ice content or unfrozen water content. For that, the scale is usually of tens of meters, if I'm not mistaken, if you want to model something using finite element and then having that as an input. But recently now we have larger simulation that covers maybe the whole country, and you still want to be able to run that. That requires different type of modeling that I'm not an expert in, but I know people can go to that scale.
Thank you for your question, Quinn. Okay, well, I'm gonna wrap this half up. So today what we did was we went over physical technologies and the different methods that are used in data collection, modeling, software, numerical modeling, the different technological advancements, and lastly, we briefly covered collaboration efforts such as Permafrost, Net, and CreateLeap. I'd like to thank everyone for joining today. I'd like to thank our moderator, Emma Cameron, and the president for helping. And we're going to be moving into a non-technical portion. So for anyone who's just looking to get first hour, then you'll receive a certificate if you ask for one. We're going to be going into more of an informal discussion with Mehdi and Stephan talking about their backgrounds and how they got into permafrost research. So feel free to leave if you have something else to go. And so anyone who does leave, have a great weekend. I'd like to thank Mehdi and Stephan for agreeing to join with us today, and we're going to move on into our informal discussion. So changing gears a little bit. Yeah, was that a question, Natalie? Or I'm sorry, I thought sorry, I saw you raising your hand. So let's start with Mehdi. How did you, would you be able to go a little bit over your background and how you ended up getting into permafrost research?
Sure. So I did my bachelor's in civil engineering and master's in geotechnical engineering back in Iran at Sharif University. And there I studied liquefaction, doing experiments. Then I came to Canada at the University of Calgary to do my PhD there on constitutive modeling, micromechanical modeling. There was no temperature, there was no ice in what I was studying. Then around 2019, I joined Colton, and but by choice, I started considering dipping a toe into maybe contributing to problems that are related more to environment in Canada. And permafrost, of course, was one of them. But what quickly happened was that dipping a toe was sucked into that field, and that's the only thing that I do now.
Was
And
there a
part of
paper or person that got you initially on that track?
yes, there was, and he's here now. He can. Stephan was one of the people that I that I got to, I had the chance to meet during my first years, and continuing our discussions over years was what one of the biggest reasons that I started studying this. And I appreciated the questions, and then found a way into it.
What about yourself, Stephan? How did you end up going down this path?
Pure chance. And when I was in high school, I specialized in physics and chemistry in Germany and wanted to study aerospace engineering or physics. But then somehow I found it very, very one-sided and figured I want something that's a little bit closer to humans. I studied physical geography, and then over time, I just tended to gravitate back to questions that were more quantitative. And sometimes looking back, I think I should have done an undergrad in, physics or engineering, because frankly, today I often don't have as much math at my disposal as I would like, and it's often very painful to do some of the things that I want to do. I've then studied in a bunch of different places. I've done, for example, a year of Arctic studies in the mid-90s in Rovaniemi in northern Finland, which, then already was heavily focused on reconciliation with indigenous peoples and like how does the Arctic work geopolitically. We had excursions into Russia at the time. I did some geoinformation management and a lot of remote sensing in the Netherlands for 1.5 years. And I never wanted to become an academic. And I kind of just got sidetracked into doing a PhD in Zurich, mostly because the people were nice and I liked climbing, and I didn't have a family to feed, and it was just a beautiful thing to do. And then I had a pretty clear coming out as, oh wow, I really love science. And I just kind of continued from there. And I think I could be in a million other different fields and just enjoy myself equally as much. What I do like about permafrost is the part of being outside, at least for part of my work, and just that it's so colorful in terms of the different disciplines that are involved. So I'd like to stay, but it could have been any other trajectory.
And at what point did you decide to kind of put more of an emphasis on collaboration in your research efforts? Or was that always part of your mandate?
I think it comes from something that is almost a little bit obsessive. When I start to work on something, there's a scope creep. So I usually start with a small problem, and then I think about like, so how have other people addressed this? And like what it could be addressed in this discipline, and I kind of keep going to, but I want to use the best possible tools and the best possible frameworks. And every question almost automatically expands into, oh, if I only work with that person, I can find much better answers.
Okay.
And let's say, where that catches fire and works really depends usually on the personal connections, right? I mean, Mehdi and I enjoy speaking with each other and, in part making fun of each other and kind of learning from each other. And that's just very, very nice. And sometimes you approach people and the vibes aren't there, right? The other person is more busy, doesn't like the vulnerability, if you want to phrase it like that, of not knowing everything. And so sometimes it works, but I think I've always loved it because there's nothing cooler than work with people who can do things that seem incredible that you don't understand really. I mean, it's phenomenal.
And I see you nodding your head, Mehdi, so that's what initially got you in that stream as well?
Oh, why? You mean why collaboration and why not doing it alone?
Yeah.
For me, it was different. It's just because I enjoy it more when you do it with others. And I think at some level, science is not done in isolation. You have to. It's a social activity, and it's an option in different fields. But I think for permafrost science and engineering, it's a must. Because the question is so big that I use this word. It has not been tamed yet. We cannot define the questions we want to answer well yet. And that part of the challenge, also part of the excitement, and that cannot be done alone.
Well, I just have, I guess, for people looking to potentially bridge that gap, or from your point of view as researchers, I know especially Mehdi, well, also Stephan, um, there's an emphasis on um, mathematical literacy. I know when I took your course, Mehdi, that was a big um, component of your course, was trying to get people to understand what they're reading and the mathematics behind it.
Mm.
Um, do you find that that's a barrier to people getting into research or collaborating because they don't understand what they're reading?
I think it's an opportunity because mathematics can help you translate things across different fields, right? It could be a common language. Um, if I know enough mathematics and uh, I'm talking to someone else who's from a different field but understand mathematics, we can translate our problems probably to a common language. It helps. And then, as I said, since we need to know what knowledge already exists. Again, for that one, you have to be able to read research, and you quickly come up with this question of being able to read technical papers. Their definitions you can understand, jargons you can quickly pick up, but then mathematics requires a background, requires some legwork before you can really pick up a paper and learn. I think I don't see it as a barrier. I see it as an opportunity that is sometimes missed.
Okay. Similar to that question, Stefan, I would ask, I know one of the things you focused on in your course was the importance of salient writing. Like you're writing very specifically, but not, you don't you don't go off and elaborate more than you need to. Um, would you say that um, would you say that papers that do that well are easier to read?
Oh, absolutely. And
It's a
like,
little bit
I'm
of a
very
softball
pleased.
question.
I'm very pleased that you find I don't elaborate too much because I think I actually have a tendency to do that. But I mean, your question follows the question about math to Mehdi, and I think, I mean, overall, if we're in research, I think we have to strive for clarity because if we are clear with, and we can be clear with words, we can be clear with figures, we can be clear with math, we can be clear in computer models. And with all of that, then we need to have a culture of asking ourselves, is what I'm doing here really the right thing? Is it reliable? Do I get to the right conclusions? And wanting to be rigorous with that. And I think clarity is part of that rigor, because if I'm not clear, I don't understand my own thoughts. When they're fuzzy, they always seem great. Um, and I think that's just a path to doing good things, is to strive for the clarity and asking yourself, am I really sure that this is better than what I had before? Yeah.
And so is there any advice you'd like to give to people looking to get involved in permafrost? Whether it's regarding technical writing um, or a focus on collaboration.
Well, I would say be fearless and learn a lot and become broadly competent. I mean, you don't have to know everything, but I think you have to know the lay of the land broadly, right? So if you study permafrost, know something about snow, know something about glaciers, know something about hydrology, know something about geotechnical engineering, like know your surroundings and know enough about the language that you can interface with people. You don't have to know everything, but like knowing some of the concepts. And like in practice, these are all rabbit holes in everyday life where you say like, oh, this is interesting. And then it kind of like go down the rabbit hole into different disciplines. And at some stage, you need to come back out.
So what would be a good starting point, you think, for people
Whatever is
with
the thing that fascinates you, but then I would kind of make sure that you know the lay of the land. And what I would also say is there is a danger. I think in English this is called like the jack of all trades or something like this, where you know everything a little bit, but nothing really, really well.
yeah, jack of all
I
trades,
think,
master of none?
yeah, maybe. So I think it's important that you find something where you say, in this, I am really going to be excellent. And additionally, there is like some excellence in like knowing the surrounding lay of the land.
Hmm.
But I have a feeling, even for practical purposes of career planning, like having a home base is very, very good. And I say that because I don't really have one, right? I'm not really all that typical for being a physical geography, but I would also not, qualify to be a civil engineer. And I think it pays to have a home discipline and then be broad.
In that vein, what is your current focus of research? And also, what do you think, what areas of permafrost research should receive more focus?
Are you asking me or Mehdi?
Yeah, sorry, Stefan.
Yeah,
Yeah.
okay, yeah. Um, I think there's a lot of permafrost research, and there's a lot of permafrost research we might not necessarily recognize as permafrost research, right? Because it's research that exists and can be highly useful for answering permafrost questions. Um, I think that the geocryology in Canada has a traditional, very strong field-based and empirical focus. And that is a strength that we shouldn't lose because in the end of the day, we need to understand, what do the things behave like and understand them in great detail.
Mm.
But I would like to see that complemented with more data analysis and more simulation and a more fluid learning together between these communities. I think currently there's a severe limitation because a lot of the field-based studies focus on individual configurations. What is it
Mm.
like here? But if we think about like a space-time continuum, right? All places in Canada or around the world with permafrost, the fewest of those are the places we actually study. And if we think about the times that we're interested in, a lot of those times are actually in the future, in conditions that we don't know yet.
Mm.
So many of the questions, many of the applied questions we're answering are questions about places and times where we don't measure. And like simulation and field-based research and all kinds of different disciplines have a role to play in how do we do this? And frankly, how do we deliver this? If we think about Canada again, but I know that we have people here from many different jurisdictions, so, impute any other place.
Mm.
How many thousands of people in Canada have studied weather or atmosphere or water in their university? And how many people have jobs that have to do with weather or water or climate? And we have weather forecasting, we have flood maps. What services do we have in Canada for permafrost or for permafrost change in the future? Considering that a third to half of the country has permafrost in the subsurface and will have persistent changes for the next decades and centuries. So I think there is something and like in infrastructure and capacity, people, bums and seats, salaried people with a mandate to deliver those things is also a way for multiple communities to come together and work on a shared object, like models or simulators accrete knowledge from different disciplines. So Earth system models were a bit of a revolution. And on a smaller scale, I think countries like Canada have to figure out that doing good research and delivering that research to the people who need it needs infrastructure. Much like marine-based Arctic research needs an icebreaker, permafrost research in a thawing world also needs some infrastructure. But because we didn't have that in the past, it's very difficult to convince people, well, now we need it. Because it's an area that no one works on. It's
Mm.
much easier for people to keep advertising their own areas. And collectively, I would like to see all of us as people with an interest in permafrost to wrap our heads around what is that and how can we make it happen?
Okay. And Mehdi, would you say that from your point of view, that geotechnical engineering, more geotechnical people involved in geotechnical engineering, structural engineering, engineering in general, let's say, should focus more on directing their research and their practice towards permafrost? Or is it a popular topic?
I think it's a nice move if they do it, because first of all, Canada is on the cutting edge of permafrost science and engineering. For structure, I'm not sure. For geotech, for conventional geotech, I'm not sure of that. Second, I would hope more people consider doing this, because we need that, right? We need people coming from different fields with different knowledge, different skills to study this, because of the urgency of it. And I think it's the correct move if to be considered for someone who can do that.
Would you say it's catching on, or it's not quite there yet?
It's difficult for me to comment on that, because I'm probably too academic to give you the right answer.
Well, like maybe Stefan, you'd be able to comment on that? Well, you kind of just did, but
Well, in terms of it catching on, I mean, there's not that many universities in Canada that have undergraduate and graduate programs in permafrost.
okay.
And when I was teaching in Zurich, it was, of course, there was glaciers and permafrost was often combined, but there were sometimes 140 people in those lectures, undergraduate. And so here, sometimes, we're teaching permafrost courses to 10 or 15 people, but it's Canada. So I somehow cannot understand, and maybe it's just me, but I cannot understand, why are we not overrun with super motivated people who say, this is a great topic. I'm game. I want to excel at this. I want to make a difference. I want to learn. I like this is like my country, my planet. Climate change matters. Northern areas matter. This is fun, motivated people. Like it's like I'm almost puzzled why we're not overrun with people who say, yeah, let's go.
I
We
think
have
we
a,
can.
we have a number of really, really cool students,
Mhm.
but I'm surprised that this is not more of a hip thing in Canada.
Well, I think
Matters.
that perfectly encapsulates everything we talked about today.